Hello, everyone. Today we'll be discussing an explicit frame construction for normalizing 3D point clouds. This is work that I've done with Shuxia Wang, Tommaso DePernix, and Bao Wang at the University of Utah. Many real-world data sets are represented as 3D point clouds. This could be molecular structures or 3D visual models. However, they can be positioned or oriented in any way without a predefined reference frame. So if I define an isometry as a rotation, reflection, or translation, then if I have some point cloud, after that, the transformation under the isometry, I have what appears to be a new point cloud. But normalization is a function that transforms the data into a unique and canonical representation, regardless of the transformation. So here we see after normalization, I have my canonical representation, which represents both of these data, these point clouds. So existing methods for normalization have some limitations. In particular, we have non-unique representations. This can be caused by things like principal component analysis. So PCA-based constructions don't guarantee that there's a unique frame for the data, and this can lead to inconsistencies in analysis. And then we can have approximation challenges, where learning methods like autoencoders might struggle to accurately represent non-continuous functions, and their generalizability can be hampered by limited data variety. So let's look at each of these limitations. So here I have two molecular structures. I have C4H2 and I have H2O. And so C4H2 is a rank 1 structure and H2O is a rank 2 structure. And what I do is I take the initial data and I transform it 3 times, and then I look at the normalization under the transform. And so we see that for PCA, it does well in the rank 1 case, but it has some non-unique canonical representations in the rank 2 case. The learning-based method, we see that struggle with approximations in the rank 1 case, but it does relatively well in the rank 2 case. So our contribution is that we introduce a training-free algorithm that achieves the unique normalization of arbitrary 3D point clouds without breaking the universality of the learning framework. So here we see these same C4H2 and H2O structures, and then our method, which we call the asymmetric unit normalization, or ASUN, applied to each of these structures. So here we see the rank 1 structure and rank 2 structure with unique canonical representation. So the challenge that we have to overcome is that inherent symmetry causes ambiguities. So here I have a point cloud with some inherent symmetries, and from these inherent symmetries arise these ambiguities. In this case, I have ambiguity up to 180-degree rotation. So I can choose any rotation up to 180-degree multiple of each other that will give me the same canonical representation. And so our solution is to simplify the data symmetry by extracting the asymmetric unit. And so here we find the asymmetric unit, which groups these symmetric elements together and forms a directed graph. And then we use this information to normalize our point cloud. If we look at our numerical evidence on molecular data, so here I'm going to allow each of the methods to choose a canonical representation. Then I'm going to transform the data and see how well that method remaps the transformed data to its canonical representation. So here we see that PCA does well in rank 1, but not well in rank 2 and rank 3. The autoencoding methods do very poorly in rank 1, but okay in rank 2 and rank 3. But asymmetric unit outperforms each of the models among all rank group data. Then if we group the data by its inherent symmetry, so maybe we have some rotational reflective symmetries, some dihedral symmetries, some tetrahedral symmetries, then we see that the asymmetric unit normalization outperforms all other models on this task. We can also look at that model data. So here we have different models. Here we're looking at airplanes, and we want to try to normalize our point clouds for these airplanes. Here we see our normalization applied in blue. Okay, and so the task here is that I give you some training data, which is not transformed, and then some test data, which is transformed, or I give you training data, which is transformed, and test data, which is transformed, or I give you training and test data, which has been normalized. Then we grouped our models by invariant and equivariant models like Schnedt, EGNN, MACE, and ESCN, or models that where we've applied this universality principle that they're invariant given that we have this asymmetric unit normalization. So this would apply to things like the graph convolutional network, GCN2, SCHNET, and EGNN, where we directly include the positional information into the invariant feature. And so what we see is that our asymmetric unit normalization can slightly improve the performance here among invariant and equivariant models, but it really boosts the performance in these universal frameworks. In particular, we see that the EGNN performance is 2x'd by this universal framework with asymmetric unit normalization. Thank you.